Today we are beginning our discussion of Chapter 7, which is entropy. Entropy is often a new concept. Most students have not worked with this in the past. So we're going to talk about some of the things that entropy means, some of the implications it has for processes and reactions and cycles in the real world, why it's important, and then tomorrow, the next lecture, we'll start to handle entropy in a mathematical fashion. So the first thing that I would like to do is to present a problem. This problem is actually, I've posted it to your Moodle page. And this, I think, is a really good implication for entropy and why it's important, if she's posted it. If not, I'll get it over here. All right. Here it is. So I'm going to ask this question. All right. And before we get started on this idea of entropy, this is something that you've probably assumed. We know how it works, but let's talk about it for a minute. If you have a pot of water and you have boiled the water off, so the water is in steam, and you've put a cylinder or a sleeve over the pot so that the steam is going to be captured. If you turn the heat off, what will happen to the steam? Will it go away? No. What will it do? Will it turn into a different substance? Will it become soap or soda pop or... No, what does it do? What's that? You know what it does. Turn off the heat, what happens? It what? It becomes water. That's exactly right. So in the natural order of things, if we have steam and we remove the source of heat, and the other part is if the room is cool enough, if we're not in a steaming hot room, if we're not in a sauna, the steam will convert to water. So with the first law of thermodynamics, we can do a balance that will tell us how much heat will be released from the steam when it condenses into water. So down here, you'll see that we have the first law of thermodynamics, which started out being Q minus W equals delta U plus delta PE plus delta KE. But there's no particular change in potential or kinetic energy. So all we're talking about on the right-hand side of the equation is delta U. And if we change this equation, we just bring the W, the work, over to the other side of the equation, we get Q is equal to delta U plus P delta V. And in our property tables, we can identify that H, or enthalpy, is equal to U plus PV. So delta U plus P delta V is just delta H. And we can then say for intensive properties, so that we don't have to worry about how much steam, how much water we have, that Q is equal to delta H. So from our property tables, we can find the H value, or the enthalpy value for steam, and we can also find the enthalpy value for water. So Q in this case is going to be equal to H2 for water, H1 for steam, and the amount is negative 2,256.5 kilojoules per kilogram. That means that for every kilogram of steam that we allow to condense into water, that 2,256.5 kilojoules of heat is released into the room or into the environment. And we are kind of assuming that the room is large enough that the temperature of the room won't change. All right, so the first thing we know is, from the first law, I'm going to write this down so that we can discuss it a little bit, that Q goes out for steam to water. And the amount is 2256.5 kilojoules per kilogram. Okay? But now let's look at another reaction. What if we have liquid water and we convert it to steam? Well, the first thing is we know what we have to do, right? I mean, inherently. We don't know this mathematically yet. But how do we get liquid water to turn into steam? we add heat. That is correct. So if we do the first law of balance for liquid, water to steam, we go ahead and we find that Q, and I have capital Q, that should actually be small q right here. Small q is equal to positive 2256.5 kilojoules per kilogram. Q goes in for water to steam, and the amount is 2256.5 kilojoules per kilogram. All right. Now, we already know this, and we've worked with this. This is just the first law, and we didn't really do a mass balance, but we know that the amount of steam, the weight of the steam, has to be the same as the weight of the liquid water. But the question that we do not know how to answer yet is, why does this happen? And the other question that we don't have the answer to is, which way? Now, when we're talking about water to steam or steam to water, it's very obvious. Water, liquid water, becomes steam if we add heat. Steam becomes liquid water if we remove heat. But what causes the heat to go in or out of the substance? So in other words, we really don't have a mathematical expression for determining which way this is going to happen. We need a mathematical expression to determine which one happens. So far, even though we may not be totally aware of this, we've just relied on our instinct, or we've relied on the fact that we know that in a cooler room that steam will condense, and we know that if we put in a bunch of heat, or if we put a bucket of water in a very, 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 very hot room, that it will vaporize. But we don't really have a mathematical expression for that. And it turns out that in order to determine which happens, water to steam or steam to water, we need another mathematical law. And it turns out that that law is the second law of thermodynamics, and we need a physical quantity called entropy. All right, now in chapter 6, we talked about this idea. We talked around this idea. We talked about it conceptually. And what we said was there were two statements. We had the Kelvin-Planck statement, and we had the Clausius statement of the second law, which was the Kelvin-Planck told us that in order to get heat in and get work out, we were going to have to expel some heat to a lower temperature reservoir. So in other words, in terms of making work, this heat is lost. And in the Clausius statement, we said in order to move heat the opposite way, we have to put work in. So that means that we can't pump all of the Q sub L out. We have to put work in to drive this cycle. So we have to drive this cycle because we're driving it backward. I'm going to say backward. So in other words, for something to happen opposite the way we want it to happen, or that it would naturally occur in nature, we have to put work in. Okay? So there's a natural direction. The corollary to this is that there is a natural direction in which processes and reactions spontaneously occur unless we drive them. And we drive them by putting in work. Okay? So that's what we're talking about with our steam and water example. We can see that the heat released or absorbed is exactly the same amount of heat. But we don't know which way it goes. And which way it goes doesn't really just depend on, it doesn't depend on the reaction at all. And that's all we've talked about. What it depends on is what's going on with the surroundings. Are the surroundings hot? Are the surroundings cold? Are we putting work into the process? Are we putting heat into the process? Those are the things that make a determination as to which way the process will go. So the idea of entropy is a little interesting. But entropy, let's see, I don't know if I want to put a definition of entropy up yet. But entropy, let's just say right now that entropy is a physical quantity that's going to allow us to use a mathematical relationship to determine the direction of a process. So, in its largest sense, entropy is a quantitative, so we need to get this back to math. We're engineers, we don't just want to talk around it, we want to get down to it and decide which way it's going to go. A quantitative measure of the microscopic disorder of a system. So if we think really broadly about this idea of disorder, in the natural universe, disorder tends, this is a statistical word, to increase, and therefore we can say entropy also increases for any real reaction. All right. Now, if you think about disorder, and I'm not really keen on this example because it's quite incomplete, but we had talked earlier in the semester about the fact that if I have a coffee cup sitting on the table, a ceramic coffee cup, and if I pick it up and I pitch it against the back wall, and it breaks into a million pieces, are the million pieces, are not really literally a million, maybe it broke into 5 pieces, maybe it broke into 6 pieces. Is the coffee cup more orderly than the pieces that I break it into? So in other words, is it less orderly, is it more disordered to have a bunch of different pieces? The answer is yes, because there's a whole bunch of ways for the coffee cup to be broken. There is only one way for the coffee cup to not be broken, which is whole. So it's more likely for the coffee cup to be broken, statistically speaking, than it is for it to not be broken. Okay? That's the way that the universe tends. So if I take the coffee cup and I throw it against the wall, and I break it into some number of pieces, that's something that could happen in the real world. I put in energy, it broke. The chances of me taking a whole coffee cup and throwing it against the wall and having it break are quite high. Not that I'm going to do it, I mean that it would break if I were to do that. What are the chances of me randomly gathering up those pieces, throwing them back on the table, and having it reassemble itself into a coffee cup? Right, well, not quite 0, but if I did it, like if I invested my entire life and took all of my, had a whole bunch of graduate students, and we took our whole lives into throwing the coffee cup up on the table, statistically, it's possible that one time it would reassemble itself into a coffee cup. Okay, coffee cup is more disordered. Broken coffee cup is less. Assembled coffee cup is less disordered, or more orderly, and therefore less likely. Broken coffee cup is more disordered, and therefore more likely. So disorder tends to increase, and I would add that it is more likely. And then sort of a phrase called likelihood of state. So things tend to proceed in a direction of less order, or to proceed in a direction that is more likely, or more likely is the best I can do. All right, and that's what we're talking about with entropy. So entropy, we always end up, because this is a really, we start to get into the idea not of conservation, but of increase. And so we try to write an inequality in a way that looks like an equation. So, entropy increasing. We start with something called the Clausius inequality, which is not exactly the same as this Clausius statement of the second law of thermodynamics, but is closely related. And what it basically says is that for any cycle, that means where we start and end at the same spot. It's the same conditions. That if we do, this symbol is referred to as a cyclic or cyclic integral of the inexact differential of heat divided by temperature for any cycle, that value will always be less than or equal to 0. And what this means, this temperature is absolute temperature. And therefore, what that means is that this value is always going to have a net effect of a negative. So if we have a very simple, the simplest cycle that we can have is where we go from state 1 to state 2 in one process, and then we come back to state 1 from state 2 in another process. And I've dotted this line for a reason that will be revealed in just a moment. Well, one of the meanings of an integral is a summation. So if I want to get rid of this weird integral symbol, we could write it as two integrals. We could write it as the integral from state 2 to state 1 plus the integral from state 1 to state 2 of these same quantities, del Q over T, for this process, 2 to 1, and this process from 1 to 2. Okay, and so what we're saying is that the sum of those two process integrals then would have to be less than or equal to 0. All right, now if we look at the process from 2 to 1, and we say this could be either reversible or irreversible, but we're going to call this one a theoretical reversible process. We can then define this as change in entropy. So since we're going from 1 to 2, we can call this S1 minus S2. And this is a definition. Okay? So if we take this integral, oops, I put that up too far, which might be reversible or might not be reversible, and we add to it the difference between these two, that's always going to be less than or equal to 0. We can rearrange this to write this as a delta. In other words, S2 minus S1. So we could say negative S2 plus S1 equals negative integral from 2 to 1 of del Q over T. And then if we multiply through by a negative 1, oh, sorry, this is not equal. This would be less than or equal to. What happens when we multiply an inequality through by a negative? We reverse the sign. And then we have this expression then that S2 minus S1 is always going to be greater than or equal to the integral of del Q over T for those same boundaries, right? We're going from 2 to 1, from 2 to 1. And we could write this as delta S then is always greater than or equal to the integral del Q over T. And it turns out that the equality happens for a reversible process. The inequality happens for an irreversible or real process. Okay?
Where did the S come from?
It's a definition, which we'll talk about in a little bit. Okay? And I'll explain that in just a second. It's a very, very good question. I just want to do one more reduction. Instead of doing deltas and integrals, I'm just going to do the first derivative of each of those. Okay, so what I get is that my ds, I don't even need to really abbreviate that, is always going to be greater than or equal to the differential or the inexact differential of q over t. So let's go ahead and talk about what S means then. S, which is defined as the property of entropy, it is defined as the integral of del Q over T for a reversible process. So we've gotten away from the idea of cycle, which was what we were trying to do. The cyclic integral or cyclic integral is a little bit weird to work with, so we wanted to write this for a process instead. All right? So we've defined S, or delta S, I guess the way I have it written here, and that would be the change in entropy, all right, to keep everything the same. So what that means is we utilize this idea of S as a comparison. Since it is defined for a reversible process, all real processes will be worse by comparison. Okay? So what that means is delta S is going to increase for any real process. Delta S will be equal to 0 for a perfectly reversible process. And if delta S decreases, that means the process is impossible. Right? So what that means is that we use delta S, which we have tabulated, which I'll describe in just a moment. We can work with it as a state property. But because it's defined for a perfectly reversible process, we can use it as a comparison to determine if a process will occur or not. So this is interesting in the sense that the second law of thermodynamics, which defines entropy as a state function, is really the only great law that I can think of in the physical world that's not an equality. It's an inequality. And our minds are really designed to look for things to balance. Same amount of mass, same amount of energy, and yet entropy increases. So because of that, we develop a term called delta S generated. And we can use delta S generated along with the change in entropy of a system and we make delta S generated, since entropy always increases, delta S generated has to be positive. But what we do is we can use it as like a placeholder in an equation involving entropy. Then we can use it in, like I said, in an equation involving entropy instead of using an inequality. And we use delta S generated as a placeholder in the equation. Then we can calculate it based on the other variables in the equation. And if it's positive, we know that the reaction can occur because entropy was generated or entropy increased. If it's equal to 0, if delta S generated is equal to 0, it means we have a perfectly reversible process, which is a theoretical limit. And if delta S generated is negative, it means the process is impossible because we never decrease entropy. Now, when we talk about increase in entropy, and I can see by the looks on your face, we've probably talked about enough today because it starts to get a little complicated. When we talk about if entropy always increases, in other words, delta S generated is always, let's say, greater than 0 for any real process. Okay. What that means is we can use this property of entropy in order to determine which way a reaction occurs. Because, but the other part I want to bring up before I do this, I'll put something that will kind of pull this all together on the computer. But if delta S generated is always greater than 0, what that means is we're going to have a change in entropy of the system, but we're still left with this del Q over T term. And what is this? Well, del Q over T refers to heat exchange with the environment. Okay, so S2 minus S1 can be either positive or negative, but del Q over T, if T is always positive, del Q over T is going to be negative if del Q is negative, and it's going to be positive if del Q is positive. So heat exchange with the environment, and it depends on whether heat goes in to the system or comes out of the system. Because since T is T absolute, it's always greater than or equal to 0. It would only be 0 for exchanging heat with the temperature of the environment if the temperature of the environment were absolute 0. So here's one other little fun fact. If you have a reservoir, meaning a heat source or sink, the definition of a heat source or sink is that it's big enough that you can exchange heat with it without changing the temperature. So if I have a cup of ice here in the room and I melt the ice, heat went out of the ice, right? But did it change the temperature of the room? No, it didn't. This is the whole idea also, like we talked a little bit about nuclear submarines. Nuclear submarines generate an awful lot of heat, but they operate in the ocean, which is really, really huge. So they generate a lot of heat, exchange it with the ocean. The ocean does not change temperatures. It changes a little bit, but it wears out. It baffles, I guess would be a non-technical term for it. All right, but so what that means for this integral, let's look at it. If it's del Q over T, if we're exchanging with a source or sink, what happens to T if it's a constant? If we're not changing the temperature of the source or sink, what can I do with it in terms of the integral? You can pull it outside, right? So that means that if T is constant, we just get the integral of del Q over T, and the integral of del Q is just Q over T. So that greatly simplifies the integral. If the temperature of the environment changes, the integral gets more complicated. We have to have heat exchange as a function of temperature, but if T stays constant, the integral simplifies mathematically. All right, so in closing, what I want to do is go back and take a look at the podium PC again. We're going to look at my ice or steam to water, water to steam problem. Okay, so we've already determined that the first law, or the energy balance, just tells me that heat goes out for steam to change into water, or heat goes in for water to change to steam. And we don't know which one's gonna happen. I mean, mathematically, we know intuitively, but we don't know mathematically what's going to happen. So what's going to tell us is the second law of thermodynamics. So let's talk about the first one, steam condensing to water. Okay, the second law, and we haven't really fully discussed these terms, but basically we have an S in and an S out and an S generated term and a delta S of the system. So if we calculate this S generated, we can say that that's going to be equal to the change in entropy of the system plus the entropy out, which is the Q over T term. So I pick up values out of the chart, delta S of the system, this is S2 minus S1. Those two added together are a negative. Q goes out of the system, so that means that my Q out, see it's negative in this equation because that's with respect to the system. It means it goes out, so Q out is positive. This term is positive because we're talking about the heat exchange with the environment. So we take that Q out, 2256.5, divided by the absolute temperature. This number is larger and positive. This is smaller and negative, so my overall number of S generated is positive. So what that tells me is this is the process that will occur. Because S generated is positive, steam will condense to water in this room. Let's look at exactly the same equation now for water vaporizing into steam. We have kind of the same idea, S generated, but now we have the final number, 7, minus the initial number, which is 1. Now we have an S going in, right, because we didn't have an S going out. Okay, so S going in is the Q into the system, and we determine that by this sign. It's positive here. So when we do that number, we see that the answer is negative. So for liquid turning spontaneously into steam, I have a negative S generated. It will not occur. For steam condensing into liquid, I have a positive S generated, which means the process will occur. So the second law can be used to determine which direction a process occurs. And you always use the second law of thermodynamics in conjunction with the first law of thermodynamics. And if we're talking about an open system, we also have to use it in conjunction with mass balance. Okay? So do you guys have any questions yet? All right, I'm going to give you one more word definition, just so that if you get started on your homework, you'll be able to understand what they mean. We know that we have this term called entropy, and if something is involved in entropy, we call it entropic. So if a process is referred to as isentropic, this is like isothermal, means the temperature stays the same. Isentropic means entropy stays the same. So if you look at this equation, you can have an isentropic system if S2 and S1 are the same, or you can have an isentropic heat exchange if there's no heat exchanged. Anytime that there's heat exchange, because this temperature is always going to be positive, unless Q exchanged with the reservoir, with the environment, is equal to 0. In other words, if it's a perfectly adiabatic process, perfectly reversible and adiabatic, then you could have an isentropic process. But any heat exchange results in a change in entropy. So in order for a process to be isentropic, it has to be adiabatic, meaning no heat is exchanged, and it also has to be reversible. Okay, oops, you probably want to see that. So the only type of process that we have, that we've defined in here that is isentropic, is both adiabatic and reversible. All right, well, that's it for today, ladies and gentlemen. I will post this video. I will have 2 more videos for Chapter 7. Continue working on your homework for Chapter 6. Turn in your homework for Chapter 5 by the end of the day. If you haven't already, I've already gotten most of yours. And we'll come back on Thursday and talk more about entropy and the second law of thermodynamics.